A stone heavier than 10 elephants once slid silently across a desert. Ancient societies built monuments that still baffle us, not with magic, but with a hidden science of movement and management. This video uncovers the 26 logistical breakthroughs that transformed wilderness into wonder. By the end, you will see these stone giants not as mysterious ruins, but as the solved puzzles of history's greatest engineers. How did planners feed a city of workers for decades in a barren place? What simple trick allowed a handful of people to walk a mountain up a hill? The answers reveal a forgotten world of ingenuity. What human achievement today makes you wonder, how did they even begin that? That silent slide across the sand began with a decision made long before the first laborer arrived. The true first step in building an ancient wonder was not lifting a stone, but understanding a place. Before any grand design could take shape, the planners had to become masters of their local environment, conducting a kind of prehistoric resource mapping that would put many modern projects to shame. This was the foundational breakthrough, the essential puzzle of logistics, answering a simple, brutal question: where do we get all of this stuff? The answer was never the closest pile of rocks. It was a deliberate, calculated search for the specific material that balanced quality with distance. For the gleaming white casing of the Great Pyramid, this meant traveling across the Nile to the distant quarries at Tura, because that limestone was finer, stronger, and could be polished to a brilliant sheen. For the raised platforms of the ancient city of Mohenjo-Daro, it meant seeking out a particular type of basalt that could withstand flooding and weight. This was not guesswork. Archaeologists like Mark Lehner point to evidence that the Giza planners likely created detailed quarry maps, a practical geology that understood which layers of stone were free of cracks, which could yield the largest blocks, and how to follow a natural seam in the bedrock. Their environmental mastery went far beyond rock. It meant reading the landscape for seasonal rivers and canals that could float stones during the flood, saving unimaginable effort. It meant identifying the firmest, most level paths through the desert to serve as permanent transport roads. They turned the entire region into a detailed blueprint, transforming geography from a formidable obstacle into their primary tool. By knowing precisely what was where, they laid the invisible foundation for everything that followed. And with that map complete, the next, more violent phase of the operation began: the monumental task of extraction. The quarries were now alive with activity, a landscape being systematically dismantled, but the stone was just raw material. The true challenge was what to do with the thousands of hands needed to shape and move it. This leads us to the second, perhaps most profound logistical breakthrough: the industrial-scale organization of labor and specialization. Forget the Hollywood image of a mindless, whipped multitude. The reality, pieced together from archaeological sites like the workers' villages at Giza, reveals something far more sophisticated: a functioning society of skilled professionals. This was not a mob, it was a meticulously structured workforce. There were draftsmen who drew precise guidelines on the stone, master stonecutters who understood the grain of granite, carpenters who built the sledges and levers, and even dedicated water carriers who kept the teams hydrated under the sun. Each person had a defined role, a specialty honed over years. This division of labor was a masterstroke of efficiency. Imagine the gain when one person spends a lifetime perfecting the art of dressing a limestone block to a perfect surface, while another becomes an expert in tying the complex knots that secured a load. They worked in rotating shifts, with records like the ancient diary of Mura showing meticulous accounts of daily activities, from delivering limestone blocks to distributing tools. This was the ancient equivalent of a corporate hierarchy, with foremen, engineers, and scribes ensuring every part of the machine meshed smoothly. They were paid not with coin, but with the most practical currency of all: bread, beer, fish, and a place to live. This system transformed a massive population from a potential chaotic crowd into a coordinated, purposeful engine. But an engine of that size requires constant fuel. Keeping this human machine running introduced the next monumental puzzle, one that dwarfed even the moving of stone. How do you feed a small city of workers for decades in the middle of a desert? The daily bread ration for a pyramid worker was not just a meal, it was a logistical miracle. You cannot feed an army of 10,000 workers with hope alone, especially when they are stationed in a barren desert far from fertile fields. The third breakthrough that made the ancient giants possible was the creation of vast, state-managed agricultural and supply economies. The true foundation of monuments like the Great Wall of China or the Roman aqueducts was not just engineering genius, but a calculated, massive surplus of food. Centralized authorities mastered the art of collecting grain taxes from across an entire kingdom, then redirecting this river of produce to permanent or seasonal work sites. In ancient Mesopotamia, temple economies kept meticulous clay tablet records, detailing exact barley rations for each laborer working on the towering ziggurats. This required far more than just successful farming. It demanded an entire support network of granaries to store the harvest, a transportation system for moving foodstuffs by river and road, and a bureaucracy of officials to manage distribution, prevent spoilage, and stop theft. The monumental challenge of feeding thousands, often in remote and inhospitable locations, was solved by creating what amounted to a state-run catering operation that lasted for decades. This system turned human energy into a calculable resource, as predictable and necessary as stone or timber. Think about what it takes to plan meals for a small city every single day, not for a week but for a generation. That scale of planning is almost unimaginable. It meant knowing precisely how many sacks of grain were in a warehouse hundreds of miles away, and coordinating their journey so they arrived just as the last batch was being consumed. This food supply chain was the silent, steady heartbeat of the entire operation, the fuel that kept the human engine running. But keeping this workforce healthy, housed, and motivated required another layer of innovation, one that focused on moving the very mountains they were building with. The rhythmic pull of 1,000 ropes begins with a single, brilliant idea. The fourth breakthrough that unlocked the movement of mountains was the systematic invention of megalithic transport technology. This was not about discovering one perfect tool, but about refining a whole toolkit of simple machines to defeat a single, immense enemy: friction. The ancient engineers became masters of reduction, finding clever ways to make the impossible weight of a stone field just a little bit lighter. We see this in the famous Egyptian tomb painting from the tomb of Jehu'tihotep, which clearly shows a massive statue being pulled on a wooden sledge, with a worker pouring liquid ahead of the runners. This was likely water or a slurry of mud, acting as a lubricant to turn a bone-shaking drag into a slick, controlled slide. But the real genius lay in combining these basic elements into a reliable system. The development of the specialized transport sledge or cradle was a revolution. This was not just a flat piece of wood. It was an engineered platform designed to distribute weight evenly and be securely lashed to the stone, turning an awkward, teetering block into a stable load that could be pulled by coordinated teams along prepared pathways. Modern experiments have proven the stunning efficiency of these methods. Engineer Mark Whitby demonstrated that a team of just 120 people could pull a 1-ton concrete block on a lubricated track, suggesting that with the right organization, moving a multi-ton pyramid block was a matter of sustained, coordinated effort, not magic. In the Andes, the Inca faced a different challenge: sheer mountain slopes. Their solution was a technique of incredible patience and clever physics. They would place a large stone on a bed of logs, then use levers to rock it forward onto the next log, incrementally walking the stone uphill in a slow, rocking dance. Each of these technologies, the sledge, the lever, the roller, shared one goal: to minimize the grip of the earth. They transformed a back-breaking, static struggle into a dynamic, rhythmic process. You can almost hear the coordinated chants, the calls of the foreman, the unified heave of the team turning chaos into motion. Yet, all this brilliant technology would have been useless if it simply sank into the mud or stumbled over rough ground. The sledges and rollers needed a stage upon which to perform, leading directly to the next critical innovation: the creation of dedicated transport highways. The sledges and rollers needed a stage upon which to perform, and that stage was an engineered landscape. The fifth breakthrough was the construction of dedicated transport infrastructure, turning chaotic terrain into a predictable, high-capacity highway. This was not about clearing a simple path. It was about building temporary roads and permanent causeways that became the very arteries of ancient construction. For the Egyptians, this meant constructing colossal ramps of mud brick, rubble, and compacted earth, some extending for over a mile from the quarry directly to the rising pyramid base. These were not just piles of dirt. Their inclines were carefully calculated, likely kept at a gentle slope of around 7 degrees to allow teams to pull their immense loads upward with sustained, manageable effort. At other sites, the commitment to this infrastructure is frozen in time. At Baalbek in Lebanon, a truly enormous stone block, known as the Stone of the Pregnant Woman, was abandoned, still resting on the meticulously prepared transport bed of smaller stones that was meant to carry it. Across the world, the Olmecs of ancient Mesoamerica may have used raised earthen causeways through dense swamps to move their colossal basalt heads, turning impassable wetlands into solid avenues. This massive investment in roads and ramps was a brilliant long-term logistical strategy. It turned the thousands of individual stone deliveries from a series of unique, treacherous journeys into a repetitive, streamlined process. Once the road was built, every subsequent block moved faster and with less risk, but these were not set-and-forget projects. They were engineered landscapes that demanded constant care. Maintaining a road used solely for moving 100-ton stones meant regular teams patching ruts, reinforcing slopes, and managing drainage to prevent washouts. This hidden cost of maintenance, the ongoing labor to keep the corridor open, was a critical part of the logistical equation. Yet, the efficiency of these stone highways was multiplied by another deceptively simple idea, one that turned a straight line into a controlled curve: the profound power of the pivot. The pivot point is where raw force meets intelligent control. The sixth breakthrough was the strategic leverage of waterways and flotation, where ancient engineers surrendered to the current instead of fighting the ground. Where geography allowed, they turned to the most efficient transport medium available: water. This was not a simple convenience, it was a complete rethinking of the problem. The Egyptians are famed for using the annual flood of the Nile as a liquid highway. The ancient diary of Murrah, a logbook from the reign of Khufu, provides stunning confirmation. It details regular voyages, transporting gleaming white Chora limestone blocks on barges directly to the pyramid construction site at Giza. This was not a one-time event, but a scheduled, repetitive supply line operating with the rhythm of the seasons. This principle was applied across the ancient world. In Cambodia, the immense sandstone blocks for the temple complex of Angkor Wat were likely floated down the Siem Reap River from quarries over 30 miles away at Mount Kulin. To make this possible, engineers had to master a new set of skills. They achieved breakthroughs in boat building, creating robust, shallow draft barges capable of carrying staggering weights. They learned to dig canals or modify natural channels, a form of prehistoric civil engineering that redirected water itself to serve their purpose. Flotation was the ultimate friction reducer. By placing a stone on a barge, they reduced land friction to almost zero, allowing the river's own energy to do the majority of the work. A team that would have struggled to drag a 50-ton block a few hundred feet on land could now guide that same block for miles with the gentle push of poles and oars. But this elegant solution came with a profound constraint. It tied the entire construction schedule to the immutable rhythms of nature. The calendar itself became the ultimate project manager. You had to quarry the stone in the dry season, shape it, and have it ready at the riverbank precisely when the waters began to rise. Can you imagine the coordination required to deliver a 500-ton obelisk, knowing your entire window of opportunity lasted only a few weeks each year? This mastery of water transport reveals a society deeply synchronized with its environment, planning not in months, but in annual cycles. Yet, this grand seasonal rhythm was built upon a foundation of countless smaller, daily rhythms, the steady, precise accumulation of material at the building site itself. A single delay in a distant quarry could echo for months across the entire operation. This immense scale of coordination over decades demanded the seventh breakthrough, the development of advanced project management and timekeeping. These were not just calendars on a wall, they were the operational heartbeat of the endeavor, a sophisticated system for turning years of labor into a predictable sequence of achievable steps. The ancient project managers possessed a long-term vision that is staggering to contemplate. They planned not for a single season, but for the reign of a pharaoh, knowing the work might outlive its original architect. To make this manageable, they broke the monolithic goal into smaller, rhythmic cycles. They mastered the agricultural calendar, scheduling the most intensive labor for the inundation season when the fields were flooded and farming communities were available for state service. This was a brilliant alignment of human and natural rhythms, turning idle time into productive momentum. But they needed more than annual cycles, they needed daily accountability. This is where we see the true genius of their administrative systems. In Mesopotamia, scribes kept meticulous clay tablet records, not just of materials but of labor. These tablets account for man days, rations issued, and even the productivity of specific work gangs. It was an early, tangible form of critical path analysis, understanding that if the delivery of cedar logs from Lebanon was delayed, the carpenters at the ziggurat site would sit idle. Every intermediate goal was a milestone, perhaps tied to a religious festival or a royal birthday, creating a cultural deadline that spurred progress. Imagine the focus required to coordinate the arrival of limestone blocks from Tura, the granite from Aswan, the copper chisels from Sinai, and the food from the Delta estates, all converging at the Giza plateau within the same few weeks. This temporal logistics was a silent ballet of scheduling, where a scribe's notation on a tablet in Memphis directly influenced the pace of a quarryman's chisel 400 miles upriver. They managed time itself as a critical resource, ensuring that the human machine never ran out of fuel, direction, or purpose. This relentless focus on schedule and sequence was made possible only by a universal language of exactness, a system that ensured every block, no matter where it was cut, would fit perfectly into the growing hole. A perfect brick from Mohenjo-Daro could fit seamlessly into a wall in a city hundreds of miles away. This silent agreement across vast distances was the eighth logistical breakthrough, the universal language of standardized measurements and modular construction. When every stone, every brick, every beam conforms to a known size, the entire process of building transforms. It shifts from a unique, artistic puzzle with infinite variables into a repeatable, almost industrial assembly. The ancient Romans were masters of this principle. Across their sprawling empire, from the damp frontiers of Britain to the deserts of Syria, they built using standardized brick sizes and modular architectural plans. A legionary engineer in Gaul could follow the same set of instructions as his counterpart in Egypt because the fundamental units were identical. This was not about stifling creativity, but about achieving breathtaking efficiency and scale. For the pyramid builders, while the core blocks were not perfectly uniform like modern cinder blocks, they were consistently sized within a predictable range. This consistency was everything. It meant the calculations for the slope of a ramp could be reused for the next 100 blocks. It meant that teams working on different faces of the structure were not constantly improvising, but following a shared, understood pattern. The benefit is profound. Imagine training a workforce of thousands. If every task is unique, training is endless and errors are frequent. But if you can teach a worker to shape one standard block, they can shape 10,000. If a lever is designed to lift a 3-ton weight, it can lift any 3-ton weight today or next year. This standardization introduced a powerful concept: interchangeability. A stone from a northern quarry could replace one from a southern quarry without halting the entire project for adjustments. The ancient Indus Valley civilization provides one of the clearest examples. Their cities are famous for bricks that maintain a consistent ratio, a precision that speaks of a centralized system of weights and measures understood across their entire culture. This logistical leap turned construction from a bespoke, one-off art into a scalable, teachable process. It created a rhythm where progress could be measured not just in height, but in the steady, reliable accumulation of identical units. Yet, this elegant system of sameness was utterly dependent on a more fluid and fragile element: the clear transmission of a single, authoritative vision. A standard is only powerful if everyone, everywhere, agrees on what it is. A grid of red ochre lines on a limestone flake held the entire future of a statue. The ninth logistical breakthrough was the evolution of architectural communication and blueprinting, a silent language that translated a grand vision into unambiguous instructions for thousands. In a world without paper or digital files, complex monuments required plans that were not just conceptual, but physically present on the ground. The evidence for this is etched into the earth itself. At the sites of ancient Greek temples, archaeologists have found precisely cut foundation trenches that perfectly outline the future building. These trenches were not dug at random. They followed the lines of a full-scale layout marked on the ground with nothing more than taut cords and wooden stakes. This was the living blueprint, a set of instructions anyone could see and follow. For the Egyptians, the system was equally ingenious. They likely used small-scale models and gridded drawings sketched on ostraca, which are broken pieces of pottery, or on smooth limestone flakes. A sculptor in a distant quarry would not be working blind. He might have a gridded sketch of a pharaoh's face, with each square representing a larger measurement on the final, colossal statue. By following the pattern square by square, he could scale up the image with remarkable accuracy, ensuring his work would fit its destined place hundreds of miles away. This translation from idea to physical guideline was the crucial step that prevented chaos. Instructions had to be so clear that a worker who could not read a single hieroglyph could still understand exactly where to place a stone. The blueprint was often etched permanently into the construction site itself, in the form of leveled foundation platforms, alignment markers, and boundary lines carved into the bedrock. This tangible system empowered decentralized decision-making. A foreman on the north side of a pyramid did not need to run to the chief architect for every minor adjustment. He could refer to the established lines on the ground. It turned a single brilliant mind's vision into a shared physical reality that an entire society could build together. But what good is a perfect plan if the final, most critical act, the lifting of the heaviest stones into their precise positions, remains an impossible feat of strength? The clear communication of the blueprint set the stage for the ultimate physical challenge. The final, most delicate act was not about moving weight, but about controlling it with absolute precision. The 10th breakthrough was the engineering of precision placement and assembly, a breathtaking summit of logistical coordination where years of effort culminated in a single, perfect moment. Imagine the scene: a multi-ton lintel stone for Stonehenge or a granite capstone for a pyramid, now suspended dozens of feet in the air. The brute force methods used on the ground were useless here. This required a new kind of finesse. One ingenious solution, hinted at in various cultures, was the sandbox method. A stone would be lowered into a wooden frame or a prepared socket that was pre-filled with dry, fine sand. By slowly draining the sand from small ports at the base, workers could lower the massive block in a perfectly controlled descent, millimeter by millimeter, until it settled with exquisite gentleness onto its waiting mates. This was patience as an engineering principle. For raising stones up the ever-growing sides of a pyramid, the evidence points to the use of massive earthen ramps that spiraled around the structure. Teams would pull the sledges up these inclines, a grueling but predictable process. At the top, however, another challenge awaited: pivoting the block from the ramp onto the building's level surface. This likely involved a system of levers, rollers, and greased pivot stones, a ballet of calculated forces where a small push in the right place could nudge a giant. The true mark of this precision phase is seen in the joinery. At Stonehenge, the massive sarsen stones were shaped with sophisticated tongue and groove joints, and even carved with subtle curves so that when locked together, they formed a continuous, graceful arch. This meant that in the quarry, years before and miles away, stonecutters were already carving the male tenon that would one day fit perfectly into a female socket they had never seen. The final assembly was the confluence of every prior breakthrough. Transport teams delivered the piece to the ramp base. Lever crews took over for the ascent. At the summit, alignment specialists with plumb lines and sighting rods would guide the final placement, their shouts coordinating the last adjustments. In that confined, elevated space, one misstep meant more than delay, it meant catastrophe. The moment when the final stone settled into its socket, when the last lintel clicked into place, must have resonated through the entire workforce, a physical confirmation that the plan, the map, the schedule, and the sweat had all been true. It was the silent, satisfying answer to a decade of questions, but for the societies that built them, completion was not an end. The logistical focus now made a profound shift from the frenzy of creation to the solemn duty of perpetual service. The final stone's placement was not an ending, but a new beginning. The 11th logistical breakthrough was perhaps the most forward-thinking of all, the creation of systems for perpetual maintenance and cult provisioning. A completed temple or tomb was never meant to be a static monument, but a living, functioning institution that required constant care and ceremony for centuries to come. The builders understood that their work would be meaningless if it crumbled into ruin within a generation, so they planned for eternity. This was achieved through the establishment of permanent endowments, vast grants of agricultural land, vineyards, and workshops whose entire output was dedicated to funding the monument's future. For the pyramids, this meant the creation of entire pyramid towns, communities whose sole economic purpose was to support the priestly staff responsible for the daily rituals, the cleaning of the causeways, and the repair of the outer casing stones. It created a self-sustaining economic loop, where the monument itself generated the resources needed for its own preservation. Administrative texts from Mycenaean palaces and Hittite archives detail this with meticulous clarity. They record the annual allotments of olive oil for lamps, specific measures of grain for offerings, and bolts of fine linen for the statues, all distributed to the sanctuary personnel on a fixed schedule. This was not charity, it was a sacred payroll. The logistical vision here stretches the mind. It was one thing to organize labor for a 20-year project, but how do you budget for 200 years? How do you create a trust fund that outlives dynasties and survives economic shifts? They did it by embedding the monument's needs into the very fabric of the kingdom's economy, making its upkeep a permanent line item in the state's accounts. This long-term provisioning ensured the structure continued to serve its spiritual and communal purpose, transforming a feat of construction into a permanently funded entity. It was a promise to the future, written not in stone but in harvests and ledgers. This astonishing level of enduring organization points to the master system that made all the other breakthroughs possible, the invisible framework that coordinated every harvest, every work gang, and every sack of grain. Every block delivered and every meal served generated a piece of information that needed to be tracked. The 12th logistical breakthrough was the birth of administrative bureaucracy and systematic record-keeping, the central nervous system of the entire operation. On a project involving tens of thousands of people and lasting generations, memory was not enough. The world's first large-scale bureaucracies emerged not from palaces alone, but from the practical need to manage these monumental builds. In this system, the scribe with his stylus was as vital as the stonemason with his chisel. From the clay tablets of Sumer detailing barley rations for ziggurat workers, to the diary of Murrah papyrus in Egypt logging limestone deliveries, to the intricate knotted string kippers of the Inca that encoded census data and resource tallies, these were not mere notes. They were the informational infrastructure that made physical infrastructure possible. This bureaucracy enabled three critical functions: accountability, coordination, and resolution. A foreman could be held responsible for the output of his gang because a scribe had recorded it. A delay in copper tools from sign could be traced and addressed through official correspondence. Disputes over materials or work assignments could be settled by referring to the official record, not by hearsay or force. This system allowed a central authority in Memphis to know the status of a quarry in Aswan and to redirect grain from a warehouse in the Delta to a worksite that was running low. It created a verifiable trail for every asset, turning chaos into manageable data. Can you truly manage a project of 10,000 people spread across hundreds of miles without a single spreadsheet? They could, and they did, by inventing the spreadsheet's ancient ancestor. This immense administrative machine, however, did not run on data alone. It required a powerful and stable source of authority to set its goals and command its loyalty, a force that could unite an entire civilization behind a single, staggering objective. A shared belief can move mountains, or at least convince people to build them. The 13th logistical breakthrough was the mobilizing power of unified ideology and social cohesion. The most intricate plans and most efficient bureaucracies would have collapsed into dust without the willing participation of thousands. For these projects to succeed, the labor had to be seen not as a burden but as a purpose. In ancient Egypt, building a pyramid was far more than a construction job. It was a sacred, national project to ensure the pharaoh's successful journey to join the eternal gods. This divine transaction was believed to be essential for maintaining Maat, the cosmic order, which guaranteed the annual flooding of the Nile, the fertility of the fields, and the prosperity of every village. Your work on the royal tomb was, in a very real sense, an investment in your own community's survival and the stability of the universe itself. This powerful belief system transformed voluntary labor during the inundation season, when farming was impossible, from a state demand into a spiritual duty. It provided the moral and social justification for the massive redistribution of grain and resources that fed the workforce. A similar ideological engine operated in the Andes under the Inca Empire. The system of mita was a rotational labor tax owed to the state, but it was deeply embedded within a worldview of reciprocity and communal obligation to both the ruler and the divine. Contributing your labor to build a temple or a royal estate was part of a social and cosmic contract, reinforcing your place in the community and ensuring the favor of the gods. This framework dramatically reduced the need for outright coercion. It fostered a sense of collective ownership and pride, turning a workforce into a community of builders with a shared, honored goal. But this spiritual engine was always paired with very practical fuel. The ideological call was answered with tangible rewards. Workers were not slaves toiling under a whip. They were participants in a grand endeavor, compensated with food, shelter, medical care, and the social prestige that came from contributing to a project of eternal significance. Archaeological evidence from the Giza workers' village shows they received high-quality cuts of meat, medical treatment for injuries, and were buried with honor near the monuments they helped raise. The question shifts from how they forced people to do this to how they motivated them. What force convinces a farmer to leave his home and haul stones for a king he will never meet? The answer lies in a potent combination of deep cultural belief and immediate practical benefit. This social cohesion was the invisible mortar that held the entire logistical enterprise together, turning a population into a unified force. Yet, even the strongest belief and the most willing workers face a universal grinding enemy: the slow, steady drain of fatigue and morale over decades. A healed fracture tells a story of care, not just construction. Beyond the powerful pull of shared belief, the 14th logistical breakthrough was a remarkably modern system of incentives, rewards, and social mobility. The ancient builders understood that ideology alone could not sustain a human being through decades of hard labor. They needed a tangible social contract. The evidence from the workers' villages at Giza is profoundly revealing. Skeletons show broken bones that were expertly set and healed, indicating access to skilled medical care. These were not disposable laborers, they were valued assets. The administrative records from Deir el-Medina, the village for the artisans building the royal tombs in the Valley of the Kings, detail a structured life with regular days off, extra rations during festivals, and even bonuses for meeting targets. Perhaps the most powerful incentive of all was the promise of a dignified resting place. Skilled workers and their families were often granted burial plots in necropolises near the very monuments they helped raise, a permanent honor linking their legacy to eternity. This created something revolutionary: a professional class of builders. A stonecutter could teach his son the craft, knowing the work provided stability, respect, and care. This was a logistical masterstroke for managing a multi-generational project. It drastically reduced turnover, allowing intricate knowledge of quarrying techniques or ramp engineering to be passed down and refined over decades. How do you maintain expertise on a project that lasts longer than a single human lifetime? You create a career path. This early form of human resource management recognized a simple truth: a cared-for worker is a more reliable, more productive one. It transformed labor from a temporary duty into a skilled profession with its own status and rewards. This system of incentives provided the steady, motivated heartbeat that kept the physical work moving forward year after year. Yet, this entire delicate ecosystem of workers, engineers, and scribes ultimately depended on a force far more volatile than stone: the unwavering support of the kingdom's ultimate authority. A pharaoh's vision for eternity could easily die with him. The 15th breakthrough was the masterful management of political will and succession planning, a delicate art of ensuring a project outlived its founder. A king's reign might last 20 years, but a pyramid took 30. This meant the continuity of a mega project across royal successions was not just a logistical challenge, it was a profound political one. The solution was to embed the project so deeply into the identity of the state that it became a national priority, transcending any single ruler. This was often achieved by weaving the monument's purpose into the core religious doctrine or dynastic tradition of the culture. In Egypt, completing a predecessor's tomb was considered a sacred filial duty, a necessary act to maintain cosmic order. A new pharaoh would often publicly commit to finishing his father's house of eternity before even commissioning his own, ensuring that decades of labor and investment were not wasted. This was more than respect, it was smart institutional economics. The mechanisms for funding and administration had to be baked directly into the permanent temple or state bureaucracy, not tied to the personal treasury of a king. By making the project a function of the office, not the man, its budget and management could survive the turbulent transition of power. Think of the great Gothic cathedrals of medieval Europe, which took centuries to build. Their continuity relied on the project being adopted by the entire community and successive bishops, turning it into a generational civic endeavor that no single patron's passing could halt. This political logistics prevented these monumental endeavors from becoming what we might call white elephants, abandoned and crumbling upon a ruler's death. It required a deep, pragmatic understanding of the local and regional economy, ensuring that the river of resources, grain, copper, labor, never dried up simply because a name on the throne changed. The true test of an ancient megaproject was not whether it could be started, but whether it could be finished by those who inherited the dream. This forward-thinking stability at the very top created the calm necessary for innovation to flourish far below, among the specialists who solved problems with their hands. A monument's true scale was measured not just in stone, but in the distance its materials traveled. The 16th breakthrough was the seamless integration of regional and international trade networks to secure exotic materials. While local quarries supplied the bulk, the most symbolically powerful elements often came from lands beyond the horizon. The fragrant cedar for an Egyptian pharaoh's solar boat journeyed from the forests of Lebanon. The deep blue lapis lazuli for a Sumerian priestess's eyes sailed from mines in distant Afghanistan. Procuring these treasures transformed a domestic construction project into a node in a vast, ancient web of commerce. This required a sophisticated secondary layer of logistics focused on diplomacy, caravan security, and complex exchange. Securing a reliable shipment of turquoise from the Sinai Peninsula was not a simple purchase. It was an exercise in ancient geopolitics and relationship management. It involved negotiating with local rulers, establishing protected trade routes, and often sending royal envoys or military escorts to ensure safe passage. The economics shifted from bulk transport to high-value, low-volume logistics, where a single chest of precious stones was worth a year's harvest of grain. This external procurement turned the rising monument into a physical catalogue of the kingdom's reach and influence. Every block of Lebanese cedar in a pyramid temple courtyard was a silent statement. It proclaimed that the pharaoh's power extended across the sea. The monument became a museum of global connections, its very substance whispering of distant mountains, foreign forests, and far-off deserts. But these exotic treasures did not arrive ready for use. That gleaming block of obsidian from Anatolia or that ingot of tin from Cornwall was raw potential. This crucial transformation introduces us to the 17th, often overlooked logistical pillar, the indispensable role of the support craftspeople and toolmakers. A copper chisel's edge lasted only a few strikes against hard granite. The 17th breakthrough was the sustained logistics for secondary industries and crafts, a hidden world of constant supply and repair that kept the primary work from grinding to a halt. The construction site was never just a place for moving stone. It was a bustling hub that sustained an entire constellation of smaller, essential trades. Coppersmiths worked furnaces day and night, hammering out new chisels and sharpening old ones. Carpenters shaped the massive sledges and the sturdy barges for river transport. Potters spun clay into the thousands of water jars needed for hydration and for mixing mortar. Rope makers twisted miles of cordage from flax or palm fiber, their product literally holding the entire operation together. This created a localized industrial ecosystem, a microeconomy entirely driven by the monument's insatiable demands. The logistical system, therefore, had to manage two parallel supply chains, one for the monument's core materials like stone, and another, equally vital, for the raw ingredients of these support crafts. This meant ensuring a steady, predictable flow of copper ore from the mines of the Sinai, timber from the Levant, flax from the Delta farms, and clay from nearby riverbanks into these satellite workshops. The wear and tear was relentless. A single stone saw, a simple copper blade embedded in a wooden frame and pulled back and forth with sand as an abrasive, would be worn down to nothing after dressing just one large block. So the system had to account for this constant consumption, this silent tax of friction and fatigue paid in metal and wood. What happens when the quarry runs out of sharp copper? The entire cutting operation stops. To prevent this, the logistics became anticipatory, not reactive. Stockpiles of ore and timber were maintained, and skilled artisans were permanently stationed at or near the site, turning their crafts into just-in-time manufacturing for the ancient world. This web of interdependent trades transformed the building zone into a buzzing pre-industrial complex, a prototype of the factory floor where every broken tool could be fixed and every spent resource replaced. Yet, the pressure of this constant demand did more than just sustain the status quo. It sparked quiet revolutions in the materials themselves. The need for a chisel that could last longer against granite likely drove innovations in alloying copper with tin to create tougher bronze. The quest for stronger rope may have led to experiments with different weaving techniques or plant fibers. The monument, in its hunger, became an engine of practical innovation, pushing the supporting crafts to become better, stronger, and more efficient. This self-reinforcing cycle of demand and refinement was the invisible muscle that gave power to the grand vision. The dolerite hammer in a worker's hand was a paradox made solid. The 18th logistical breakthrough was the quiet revolution in material science and tool technology, where the very instruments of construction evolved to meet the impossible demands of the project. This was not just about moving mountains, but about inventing better ways to shape them. Consider the central puzzle. How do you cut and dress a block of granite, one of the hardest stones on Earth, using tools made from materials that are, by definition, softer? The answer lies in a profound understanding of applied physics and relentless experimentation. The ancient Egyptians used pounders made of dolerite, a dense, igneous rock, to slowly pulverize the granite surface grain by grain. It was a process of incredible patience where force was applied not to cut, but to abrade, wearing the stone down through thousands of repetitive, focused strikes. This was efficiency born from a deep knowledge of material properties, choosing the right rock for the right job. Similarly, the invention of the bow drill, a simple device that could generate consistent rotational force, allowed for precise boring of holes for levers or for splitting stones along controlled lines. But the most dramatic innovations often came from watching the environment itself. In many cultures, quarrymen mastered the technique of thermal shock. They would light fires directly against a stone face, heating it intensely, and then suddenly douse it with cold water. The rapid contraction caused the rock to fracture along clean, predictable planes, a brilliant harnessing of natural forces to do the work of 1,000 chisels. These tool-based breakthroughs were matched by revolutions in the very glue that held everything together. The Egyptian development of high-quality gypsum mortar, or the Roman invention of hydraulic concrete, known as opus cementitium, were logistical game changers. This concrete could set underwater and cure into a mass stronger than many natural stones, freeing builders from the slow, precise fitting of heavy blocks. It allowed for new, fluid architectural forms like domes and arches, and dramatically accelerated construction timelines. The logistics of supply shifted from delivering endless carved blocks to delivering the ingredients for this artificial stone, a more compact and manageable cargo. Each of these incremental improvements in the hardware of construction, from a sharper copper alloy to a faster setting binder, compounded over generations. A technique perfected in a quarry for one pharaoh's obelisk became standard practice for the next king's temple, creating an accelerating curve of capability. This was a process of continuous, on-the-ground problem-solving, where the challenges of the monument itself forced the invention of the tools needed to build it. The silent conversation between a worker and his material, the trial and error in a dusty workshop, these were the laboratories where the logistics of creation were fundamentally rewritten. Yet, even the hardest dolerite pounder or the most ingenious lever system had limits imposed by a far more unpredictable force, the relentless turning of the seasons and the mood of the sky above. The relentless sun and the driving rain were not just obstacles, they were active participants in the build. The 19th logistical breakthrough was the sophisticated adaptation to and mitigation of environmental challenges, where ancient engineers became master negotiators with the natural world. They understood that logistics was not just about moving materials, but about managing the very climate and geology that surrounded them. This required a deep, observational science of place. In the cloud forests of the Andes, the builders of Machu Picchu faced torrential seasonal rains. Their response was not to fight the water, but to guide it. They constructed an intricate, multi-layered drainage system beneath the city, with stone-lined channels and careful terracing that directed runoff away from foundations, preventing catastrophic landslides and preserving the site for centuries. This was proactive environmental engineering on a grand scale. In the floodplains of Mesopotamia, where mudbrick could melt away in a downpour, they discovered the power of bitumen, a natural tar, using it as a revolutionary waterproofing agent to shield their ziggurates from the elements. But the most profound adaptation was often temporal, not physical. The entire construction calendar was a dance with the seasons. Work was scheduled to avoid the Nile's inundation or the Andean rainy season, times when labor was available from farming communities and when transport by water was easiest. This was logistics built upon a deep forecasting of natural cycles, a form of ancient risk management that accepted some forces were too great to confront directly. They had to design for resilience, knowing a project could be delayed for a decade by a series of poor harvests or unusual weather. How do you build a structure meant to last for eternity in an active earthquake zone? The answer, seen in the precise, interlocking stonework of the Inca, was to create buildings that could sway and settle without collapsing, a literal flexibility engineered into the very joints of their architecture. This environmental logistics demanded constant vigilance and flexible plans B and C, where a sudden sandstorm in the desert or a week of unseasonal rain required an immediate shift in tasks, moving work indoors to carving or tool maintenance. It acknowledged the ultimate, humbling constraint that underpinned all others, the finite limits of human and animal power, a force that could be organized and directed, but never truly exceeded. This recognition of natural limits would eventually push them to seek a new kind of partner, one that could multiply their strength beyond the simple pull of a rope. The rope grew taut not from 100 straining arms, but from the steady, patient pull of a single ox. The 20th breakthrough was the calculated use of animal power and mechanical advantage, a deliberate partnership that extended human strength into the realm of the superhuman. While the coordinated effort of people remained the foundation, the ancient logisticians knew when to call in reinforcements from the animal kingdom. In Mesopotamia, teams of oxen were harnessed to drag the heaviest sledges bearing glazed bricks for ziggurates. In Egypt, these powerful animals were used in a more ingenious way, turning massive, creaking water wheels called sakias to drain floodwater from deep quarry pits, allowing work to continue year-round. For lighter, repetitive tasks, the humble donkey was the unsung hero of the supply chain, forming endless caravans that delivered food, water, and copper tools to remote sites. The true innovation was not merely having animals present, but fully integrating them into the logistical machine. This meant planning for their needs with the same precision as for the human workforce. Vast quantities of fodder had to be grown, harvested, and transported. Rest cycles and veterinary care were essential, as a lame ox could delay an entire hauling team. The animals became another type of specialized labor, their strength a predictable, schedulable resource. Yet the most profound force multiplier did not eat or sleep. It was the elegant application of physics through simple machines. Consider the shaduf, a counterweighted lift used along the Nile for centuries. With a graceful swing, a single farmer could raise a heavy bucket of water from the river to an irrigation channel with minimal effort. This same principle of mechanical advantage was scaled up dramatically on construction sites. The capstan, a rotating drum turned by men or animals walking in a circle, could wind in a heavy rope with incredible controlled force, hauling stones up an incline. The introduction of the simple pulley redirected force, allowing teams to pull downward, using their own body weight to aid the lift, a far more efficient motion than trying to pull upward. These devices were silent revolutions. A task that might have required 100 men straining in unison could be accomplished by 20 men operating a well-designed capstan system. What is the value of a single ox? It is immense. But what is the value of a well-placed pivot point or a cleverly wound rope? It is transformative, turning impossible weight into manageable force. This meticulous management of energy, both animal and mechanical, created a rhythm of work that conserved human stamina for the tasks that truly required precision and skill. And this careful orchestration of energy was mirrored in the very layout of the world the builders inhabited each day, in the deliberate design of the work camp itself. The distance from a worker's bed to the pyramid's base was a calculation of pure efficiency. The 21st breakthrough was the deliberate, planned layout of worker settlements and on-site logistics, where the very geography of the construction camp was engineered to eliminate wasted time and motion. This was not a haphazard shantytown that grew up around a worksite. It was a purpose-built miniature city designed with one goal: to keep the human machine running smoothly. At Giza, the gallery-style barracks for rotating work crews were positioned a mere few hundred meters from the southern edge of the pyramid plateau. This strategic placement meant a worker could rise, eat his morning ration, and be at his assigned station in minutes, not hours. His energy was preserved for the task, not spent on a long, draining commute under the desert sun. On the worksite itself, this spatial logic was applied with even greater precision. Zones were clearly demarcated, a form of ancient industrial zoning. There were dedicated areas for the final dressing of limestone blocks, where masons could work without being jostled by passing transport teams. Separate, centralized stations were set up for the constant sharpening of copper chisels, ensuring a steady flow of sharp tools to the cutting faces. The distribution points for daily food and water rations were placed at logical intersections, preventing bottlenecks and chaotic scrambles. Even sanitation was meticulously planned, with strategically dug latrines and designated waste disposal areas located downwind of the living quarters. This attention to public health was a logistical necessity, a critical factor in maintaining a stable, healthy workforce over decades, not just seasons. Where do you place the kitchens to feed 10,000 people efficiently? The answer was calculated, positioning them to minimize the distance food had to be carried while keeping smoke and fire risk away from storage areas. This spatial order was more than just convenient, it was a powerful tool for management and control. A foreman could glance across the organized site and immediately understand the flow of activity. A new worker could be oriented quickly because the logic of the place was self-evident. By eliminating cross-traffic and confusion, the layout itself enforced discipline and rhythm, turning a potentially chaotic swarm of activity into a coordinated, flowing process. Every footstep saved across a 20-year project added up to months of recovered labor. This ancient urban planning reduced friction in the system as effectively as water reduced friction under a sledge. Yet, within this meticulously ordered physical world, another, more abstract element required even more careful management: the constant stream of information that guided the work and the inevitable human errors that threatened to derail it. A half-inch error at the base becomes a 10-foot disaster at the peak. The 20-second breakthrough was the development of rigorous systems for quality control, error correction, and iterative learning. On a project where a single misplaced block could compromise an entire wall, mistakes were not just embarrassing, they were catastrophically expensive in time, materials, and morale. So the ancient builders engineered processes to catch errors early and adapt when they inevitably occurred. One of the most common techniques was test fitting. Before a multi-ton lintel was ever hoisted into the air, it would be meticulously dressed and trial assembled with its supporting stones on the ground. This dry run allowed masons to check the joinery, ensure a perfect fit, and make any final adjustments while the stone was still accessible. It was a simple rule: measure 100 times, lift once. For alignment, they relied on timeless tools of precision: the plumb bob and the sighting rod. A weighted string hanging from a frame established a true vertical line, while long, straight rods allowed supervisors to sight down a wall under construction, checking for any bow or deviation across its entire length. These were the ancient equivalents of laser levels, providing a constant physical reference against which every stone was judged. Yet, even with these precautions, errors happened. The evidence is etched into the monuments themselves, offering a clear window into their problem-solving process. The most famous example is Egypt's bent pyramid. Early in its construction, the structure began to show signs of instability, likely from settling or flawed foundation calculations. The builders did not simply press on, hoping for the best. They made a dramatic mid-course correction, altering the angle of the upper sections to a steeper, more stable slope. This was not a failure, but a brilliant, adaptive response, a process of real-time iterative learning written in stone. Each project became a living textbook. When a new quarry technique yielded larger, more stable blocks, that knowledge was preserved. When a particular ramp design proved inefficient, it was noted and improved upon for the next project. This institutional memory was a priceless logistical asset, stored not in archives but in the hands and minds of master craftsmen and passed down through formal apprenticeships. A young worker learned not just how to cut stone, but why certain cuts were made, which methods had failed in the past, and how to adapt when the plan met reality. Quality control, therefore, was never about achieving an abstract perfection. It was about managing tolerances, understanding what level of variation the design could absorb, and having the wisdom to know when to adjust the stone and when to adjust the plan. This adaptive capacity, this resilience in the face of the unexpected, was the true hallmark of a mature logistical system. It was a system robust enough to handle not just the daily challenges of construction, but the most profound transition of all, the moment when the work finally, after decades, came to an end. The last stone set was not the final entry in the ledger. The 23rd breakthrough was the meticulous logistics of project demobilization and site repurposing, a managed wind down as complex as the build itself. An operation of this scale could not simply stop. It had to be carefully unwound to prevent economic and social collapse. Imagine the sudden silence if 10,000 workers were simply dismissed at once, with no plan for what came next. The ancient state avoided this shock through a phased, intelligent transition. The most visible symbol of this process was the fate of the colossal ramps. These mountains of earth and brick were not left to erode. They were systematically dismantled, their valuable material harvested. The mud bricks could be crushed and reused for local housing, the timber repurposed for smaller civic projects, and the compacted earth redistributed to farmers' fields. Nothing was wasted, it was all cycled back into the economy. The human element was handled with equal care. The most skilled artisans, the master stonecutters and engineers, were often formally transferred to the next royal project, their hard-won expertise becoming a national asset. Seasonal laborers returned to their villages with their obligations fulfilled, often with a small surplus from their rations, reintegrating into the agricultural cycle. The administrative bureaucracy did not vanish. It scaled down, transforming from a construction office into a permanent endowment management team, overseeing the ongoing rituals, repairs, and security of the now completed monument. This demobilization logistics was a masterstroke of economic foresight. It prevented a regional depression by avoiding a sudden stop in the flow of food and wages. It turned a single, monumental burst of activity into a sustained, lower-level maintenance economy that could support a community for centuries. How do you disband an army of builders without causing social upheaval? You give them a pathway home, you repurpose their tools, and you transform their workplace from a site of creation into a site of perpetual service. The final, careful act was ensuring the machine that built the wonder did not shudder and break when its primary task was done. This entire civilization-spanning endeavor, however, from the first surveyor's line to the last administrator's scroll, rested on a foundation more crucial than any quarry or ramp, a foundation that was itself a living, engineered landscape. The water that carved the canals also carved the stones. The 24th breakthrough was the profound symbiosis with agricultural innovation and land management. The river of grain that fed the builders did not flow by chance. It was the direct product of another parallel logistical revolution happening in the fields. In Egypt, the state orchestrated the digging of vast irrigation canals to extend the Nile's life-giving flood, turning more desert into predictable, fertile breadbaskets. In Mesopotamia, the same administrative minds that planned ziggurats also coordinated the maintenance of complex canal networks, ensuring barley yields could support both cities and construction crews. Half a world away, the Inca transformed entire mountainsides with their breathtaking terrace systems, creating stable, productive farmland from steep slopes to fuel their own imperial ambitions. These were not separate endeavors. The agricultural mega-project and the architectural mega-project were two expressions of the same centralized, organizing intelligence. They required the same things: massive coordinated labor, long-term planning, and a bureaucracy to manage it all. The food logistics and the stone logistics formed a single, interdependent engine. A drought that crippled the harvest would starve the worksite within months. Conversely, a collapse in royal authority at the monument would shatter the system that maintained the canals, dooming the farms. This symbiosis reveals a fundamental truth: the greatest monuments were not isolated acts of vanity, but the pinnacle outputs of entire, highly organized civilizations operating at their peak. They are the most visible symptom of a society that had mastered the art of large-scale coordination across every domain. Can you truly have a pyramid without a pyramid-shaped society, one with a broad base of agricultural producers, a middle layer of administrators and specialists, and a singular apex of authority directing the whole? This deep integration challenges us to see these wonders not as alien artifacts, but as profoundly human achievements, the ultimate testaments to what a society can accomplish when it aligns its resources, its people, and its vision toward a single, staggering goal. The stone giants did not rise in spite of their civilization, they rose because of it. The sound of chisels would sometimes be replaced by the sound of drums. Beyond the precise calculations of rations and ramps, the 25th breakthrough was the deliberate orchestration of psychological and communal rituals to sustain morale. A workforce could endure back-breaking labor for a season out of duty, but to sustain that effort for decades required something deeper: a sense of shared purpose and belonging that was actively cultivated. This was morale managed as a logistical resource as essential as timber or water. Leaders understood that the human spirit, not just the human body, needed scheduled maintenance. So they planned for it. Regular festivals tied to the agricultural calendar or royal anniversaries would bring a halt to the usual toil. These were not mere days off. They were grand, communal feasts where the usual rations were supplemented with special treats. Music filled the air and stories were shared. Religious ceremonies conducted right at the building site, perhaps to honor a patron deity of craftsmen, directly linked the day's labor to a cosmic narrative. Imagine a priest standing atop the growing pyramid base, leading a chant that connected the hauling of a limestone block to the sun god's journey across the sky. In that moment, the worker was not just moving rock, he was participating in a sacred act that held the universe in balance. This psychological framing was powerful. Friendly competitions between work gangs, perhaps to see who could dress a block fastest or pull a sledge furthest, would have channeled natural rivalries into productive energy, fostering camaraderie and pride. Storytelling around evening fires allowed veterans to pass down the lore of the project, turning new recruits into the next chapter of a living epic. These rituals were logistical events in their own right, requiring planning, resources, and time. Extra beer and meat had to be allocated, space cleared for gatherings, and perhaps even temporary stages built. The investment was calculated because a united, motivated workforce was exponentially more efficient than a dispirited one. How do you make hauling a stone for the 1000th time feel new? You wrap it in a story that makes the labor itself an honor. This constant tending to the communal spirit was the invisible mortar between the stones, the element that transformed a monumental engineering project into a shared cultural journey. It ensured that when the final capstone was set, the people below felt it was their achievement too, a story they would tell for generations. And this profound sense of shared legacy points toward the final, overarching system, the master framework that made all 25 breakthroughs not just possible but coherent. The most valuable tool on any ancient worksite was not a chisel, but a memory. The 26th and final breakthrough was the preservation and transmission of this hard-won logistical knowledge, ensuring that the genius of one generation did not vanish with the setting of its final stone. The techniques for moving mountains, organizing thousands, and managing decades-long projects could not remain the secret of a single architect or king. They had to become part of a living cultural toolkit, passed down through time like a sacred inheritance. We see this legacy in the formal engineering manuals of the Roman legions, detailed texts that standardized everything from camp construction to bridge building across an empire. We see it in the closely guarded traditions of medieval masons' lodges, where master builders taught apprentices the secrets of geometry and stress that would raise the great cathedrals. In the Andes, the knowledge of how to fit stones without mortar was preserved in oral traditions and practical apprenticeships, a chain of teaching that linked master to apprentice for centuries. This system of transmission meant that each new project did not start from zero. A builder did not have to rediscover the ideal slope for a ramp or the strongest knot for a harness. He inherited them. The monuments themselves became the ultimate silent textbooks. A medieval engineer gazing at the soaring arches of a Roman aqueduct was not just seeing a ruin, he was reading a masterclass in load distribution and hydraulic engineering. The continuity of this practical wisdom is perhaps the most profound logistical triumph of all. It created an unbroken chain of applied innovation, where a solution forged in the desert sun of Giza could, centuries later and continents away, inspire the raising of a spire toward the heavens. The true monument was never just the pile of stones. It was the accumulated, shared knowledge of how to build it, a legacy that turned isolated wonders into a conversation across time. These silent stone giants are more than monuments to power. They are the frozen echoes of history's most sophisticated logistical operations. We have traced the 26 breakthroughs that transformed wilderness into wonder, from the first surveyor's line in the sand to the final demobilization of a workforce. The story they tell is not of magic but of meticulous management. The true marvel is not the weight of the stone, but the staggering weight of the organization behind it. These societies mastered the flow of materials, information, and human energy on a scale that rivals our own modern mega projects. They were not primitive mystics, but brilliant systems thinkers, engineers, and managers whose greatest creation was the invisible machine that built the visible wonder. By unraveling their logistical genius, we reclaim a fundamental truth about our ancestors. They faced impossible problems and solved them with patience, coordination, and an understanding of their world that was both profound and practical. Their achievements stand as a timeless challenge to us. They ask us to consider what we today can build when we unite clear purpose, meticulous planning, and collective human effort. Look at the skylines and infrastructures of our own world, the bridges, the space stations, the digital networks. They, too, are built on layers of hidden logistics. What breakthroughs will future civilizations uncover when they study the skeletons of our cities? What will they say about how we moved our own mountains? If this journey through ancient ingenuity has reshaped how you see these stone giants, share your thoughts in the comments below and subscribe to continue delving into the profound mysteries of our shared human past.